We are from group 1 going to talk the background of the study, which is our title is iron catalyst used in the ammonia production. The Haber-Bosch process developed in the early 90s by Fritz Haber and Carl Bosch. This revolutionized agriculture by providing a reliable method synthesizing ammonia, which is a key ingredient in fertilizer. First industrial chemical process using high pressure transformed the agriculture through ammonia-based fertilizer. This produced over 160 million tons of ammonia annually, which accounts for more than 2% globally. Based on our population growth and food demand, they predict that 8.5 billion by 2030, 97 billion by 2050, and this estimate at 10.9 billion by 2100. This must be increasing food demand crucial for the combating hunger and malnutrition. Chemical reaction, which convert the atmospheric nitrogen to produce ammonia, which is 3H2 plus N2 produce 2NH3. Now, this production requires high pressure, which is between 200 to 400 atmosphere pressure, and the temperature needed is between 400 to 650 Celsius. This production requires iron catalyst. Now, the importance of the catalyst using in the ammonia production is a critical component in the Haber-Bosch process because of the iron catalyst. It facilitates the reaction by lowering the activation energy. The iron catalytic activity allows for the breaking of the nitrogen triple bond, which otherwise pose a significant energy barrier. The efficiency of the process can enhance through the addition promoters, such as using potassium oxide and aluminium oxide. These promoters improve the catalyst durability and effectiveness, thus optimizing the ammonia production. Iron, being the most widely used catalyst, is preferred due to its robustness in cost effectiveness. Now, I will pass to our second presenter, Nur dari Iron.
So now, I will proceed with type of catalyst and catalyst property. Type of catalyst used is heterogeneous catalyst, and its application is hydrogenation. As for catalyst property, which is in our case would be iron properties, in general, iron is ductile and malleable. It comes with a silvery white and grayish metal. Iron's melting point is at 1536 degrees Celsius and it boils at 2861 degrees Celsius. Iron is three of the natural occurring magnetic elements. The other two elements are nickel and cobalt. So now we will explore the pivotal role of iron catalyst in the Haber-Bosch process, a cornerstone in industrial ammonia production. Properties is catalyst composition. The iron catalyst is primarily derived from magnetite, which undergoes a reduction to form a metallic iron. This process creates a porous structure which is a high surface area essential for catalytic activity. Promoters such as potassium hydroxide (KOH) are being added to the mix to enhance the catalyst efficiency. Our second catalyst is surface characteristic, which means the high surface area of the iron catalyst provides numerous active sites for the absorption of nitrogen and hydrogen molecules, facilitating their dissociation, which is a critical step in forming ammonia. Our third properties is enhance the promoter function. These promoters are being incorporated into the iron mix to aid the process by increasing its activity and selectivity. Potassium will act as an electronic promoter, which enhances the absorption of nitrogen, which will then improve the reaction rates. Aluminium promoters will then serve as a structural promoter, which will maintain the catalyst integrity by preventing sintering. So our last properties will be the iron catalyst operational stability. The iron catalyst is designed to maintain its activity under the high temperature and high pressure condition typical of the Haber-Bosch process. However, it is vulnerable to poisoning by impurities such as sulfur and chlorine compound, which can irreversibly bind to active sites. Therefore, feed gases must be purified to maintain the catalyst longevity. In summary, the iron catalyst composition, surface characteristic, and the strategic use of promoters are crucial in optimizing the Haber-Bosch process. Ongoing advancements continue to enhance its efficiency, underscoring the catalyst engineering significance in industrial chemistry. Next, I will pass our presentation to Hanis.
Now, I will continue for classification of catalysts. Catalysts for ammonia synthesis are critical to the efficiency and success of the Haber-Bosch process. These catalysts can be classified into three main catalysts, which is base catalyst, promoted catalyst, and supported catalyst. The base catalyst is the primary component that facilitates the reaction. In ammonia synthesis, this is typically pure iron derived from pegmatite. Iron is chosen because of its ability to provide active sites where nitrogen and hydrogen molecules can adsorb and react. Iron's unique electronic properties make it particularly effective in weakening the strong triple bond in nitrogen molecules, a critical step in the synthesis process. However, pure iron alone is not ideal for industrial use because it may suffer from limited activity and stability under the high temperature and high pressure conditions of the Haber-Bosch process. To enhance the performance of the base iron catalyst, promoters are added. Promoters are small quantities of additional elements or compounds that improve the efficiency, stability, and longevity of the catalyst. The key promoters used in ammonia synthesis including first, potassium. This is an electronic promoter that increases the electron density on the surface of the iron. This facilitates the adsorption of nitrogen molecules, making it easier to break their strong triple bonds. Second, aluminium. Aluminium acts as a structural promoter. It improves the thermal stability of the catalyst and prevents sintering, a process where a small catalyst particles fuse together and lose their active surface area. Third, calcium. Like aluminium, calcium enhances the structural stability and ensures that the catalyst remains effective over prolonged periods of operation. Together, these promoters transform the base catalyst into a more efficient and robust system, capable of sustaining high reaction rates under extreme conditions. In modern application, the catalyst is often supported on materials like alumina or other ceramics. These support materials serve two key purposes, which is they provide a high surface area for the dispersion of the iron catalyst, ensuring maximum exposure of active sites for the reaction, and they enhance the mechanical strength and durability of the catalyst, allowing it to withstand the rigors of industrial scale ammonia production. The classification of catalysts for ammonia synthesis highlight the evolution of technology and material science in this field. Base iron catalysts form the core of the system, while promoters enhance their performance and support improve their structural integrity. This synergy ensures that ammonia synthesis remains efficient, cost-effective, and sustainable in meeting global agricultural and industrial demands. So next, I will pass to the next presenter, which is Siti Shazlana.
Now, I will continue to explain about mechanism of iron catalyst in ammonia production. Today, I will explain the critical role of the iron catalyst in the Haber-Bosch process, which is used to produce ammonia. At the heart of this process is the iron catalyst, which starts as iron oxide. It gets activated by reducing it into metallic iron. This metallic iron produces unnecessary landing spot for the chemical reaction to happen. Here's how it works. First, nitrogen gas lands on the surface of the iron. Nitrogen molecules are tough to break apart because of their strong triple bond. The iron helps weaken and split this bond, making nitrogen reactive. Next, hydrogen gas also lands on the iron surface. The hydrogen reacts with the reactive nitrogen atoms to form ammonia. Once ammonia is formed, it detaches or dissolves from the iron surface, freeing up space for new nitrogen and hydrogen molecules to repeat the process. Now, let's talk about structural promoters like aluminum oxide, calcium oxide, and potassium oxide. These materials play a supporting role. They make the iron catalyst more stable and active, preventing it from breaking down under the extreme condition of high temperature and pressure. In summary, the iron catalyst is the key player in breaking nitrogen tough bond and combining it with hydrogen to produce ammonia, while the promoters ensure the catalyst stays strong and efficient. That's the magic of Haber-Bosch. Next, I will pass to the next presenter, which is Afika Sahira.
Today, I will be discussing the environmental benefits of iron catalysts and how they contribute to sustainability and green technology. Let's explore the emission, minimizing pollution, and supporting long-term industrial process. Firstly, by increasing energy efficiency and reducing carbon emission. Iron catalysts are highly effective in increasing energy efficiency and reducing carbon emission, which are a major contributor to climate change. Firstly, iron catalysts are highly effective in increasing energy efficiency and reducing carbon emission, which are a major contributor to climate change. Iron catalysts work by lowering the activation energy required for chemical reactions. This eliminates the need for high temperatures and pressures, significantly reducing energy consumption. By using less energy from fossil fuels to generate electricity, the overall carbon footprint is reduced. As a result, this process produces fewer greenhouse gas emissions, which is a key step in combating global warming. Next, iron catalysts have an impressive lifespan, lasting for several years in industrial application. Their durability ensures that they can endure repeated use without needing frequent replacement. For example, in the Haber process, which synthesizes ammonia, the same iron catalyst can be used over long periods, reducing the need for additional resources and manufacturing. This aligns with sustainability principles by conserving natural resources and minimizing the environmental impact of producing new materials. Additionally, by incorporating recyclable substances, iron catalysts further reduce waste and help manage hazardous industrial byproducts effectively. Lastly, iron catalysts help to minimize pollution across various stages of their life cycle. Iron is one of the most abundant elements on Earth, meaning its extraction does not require extensive mining or refining. This prevents the environmental degradation often associated with rare or toxic elements. Furthermore, iron is non-toxic and safer compared to other materials, making it an environmentally friendly choice. From mining to disposal, the use of iron catalyst significantly reduces pollution, ensuring a cleaner process overall. In conclusion, iron catalysts are a remarkable tool for promoting environmental sustainability. They help lower carbon emission, offer long-term usability, and minimize pollution throughout their life cycle. By adopting iron catalysts in industrial process, we can take meaningful steps towards greener and more sustainable solutions. Thank you.